Thanks for your watching this video. The topic of this paper is FRI sampling for ultra-wideband Gaussian process based on non-ideal LPF. This presentation consists of research background, problem formulation, FRI sampling for ultra-wideband Gaussian process based on non-ideal LPF. Handwave Prototype, simulation experiments, and finally a short conclusion. The ultra-wideband Gaussian process means ultra-high bandwidth, according to the traditional Nyquist sampling theorem. The sampling rate must be greater than twice the highest frequency of the signal, so that the orange signal can be restricted without distortion. So sampling an ultra-wideband signal requires a very high sampling frequency, which is difficult to achieve. In order to effectively reduce the sampling frequency of signal and restrict the orange signal, many experiments have carried out a series of research on the sub-Nyquist sampling methods. Finite rate of innovation sampling theorem is a feasible solution to reduce the sampling frequency of ultra-wideband Gaussian process whose base process is known. Some of the FRI sampling systems did not propose specific Handwave implementation scheming, and some did not consider the impact of non-ideal effects in Handwave implementation. In actual design, LPF is usually used as the sampling kernel function. This is a non-ideal effect between the ideal LPF and the non-ideal LPF, which is bound to have a bad influence on the restriction actually. So we propose a new FI sampling for ultra-wideband Gaussian process based on non-ideal LPF. With the classic FI sampling system, which is shown in figure, taking the basic sync sampling kernel as an example, we modeled the process of FRI sampling and the restriction of the ground penetrating radar ultra-wideband Gaussian process. We give a XT signal model, where HT is a non-Gaussian process waveform. AL, TL correspond to the amplitude parameter and time delay parameter of the detected process respectively, and T is radar process repetition interval. However, in the Handwave implementation process, ideal LPF is non-existent. It will bring non-ideal effects and affect the restriction accuracy because the filter cannot achieve the same effect of simulation. In order to eliminate non-ideal effects caused by non-ideal LPF, we proposed a new FI sampling for ultra-wideband Gaussian process, which is based on non-ideal LPF. The proposed FI sampling framework has been shown in figure, and it has two parallel channels. Each channel is divided into a non-ideal filtering stage, a loss-bit sampling stage, and a quantization stage, after which the unknown parameters are restricted using estimation algorithms. The frequency response of a non-ideal filter is written as the GT use impulse chain signal as a sampling signal, which can be written as a random combination of the T, where T is a sample interval. Input signals SD and HT, YT and HT can be obtained from the sampling structure, and then samples can be obtained after quantization. But those sampling Yn and Hn contains no ideal in phase caused by no ideal LPF, which can lead to low restriction accuracy. We design a new estimation algorithm to eliminate no ideal in phase by these samples. The new estimation algorithm can be summarized as theorem 1, and the proof process is given. Consider Gaussian process XD, where the basis function ht is known. Assume that these two signals are input the above proposed system. Then we can obtain that the samples are given by Yn and Hn respectively. If the sampling frequency satisfies the Fs greater than 2 twice F, where F is the cutoff frequency of non-ideal LPF. Finally, we can estimate the delay parameter and the altitude parameter from those samples unique under high precision. According to the Convolution Theorem, the CTFT of orange signal channel can be gotten. It is obvious that when omega is a point signal and the point is omega s is equals to times pi divided ts. When the sampling frequency satisfies Fs greater than 2 times F, where F is the cutoff frequency of non-ideal LPF. According to the Nyquist sampling theorem, we can avoid frequency aliasing, and its frequency domain information can use a pointer to complete it. According to the Convolution Theorem, the CTFT of base signal channel can be gotten. It is obviously that H omega is a point signal and the point is omega s equals 2 times pi divided ts. When the sampling frequency satisfies Fs greater than 2 times F, where F is the cutoff frequency of non-ideal LPF. According to the Nyquist sampling theorem, we can avoid frequency aliasing, and its frequency domain information can use a pointer to complete it. Because SD is a linear combination of different delay parameters and altitude parameters of HD, there is a central relationship between them in the frequency domain. Dividing the frequency of 10 samples can eliminate the non-ideal effects caused by non-ideal fields, and simplify them into a typical parameters estimation problem. We can solve it by annihilation filter algorithm. Because in the hardware implementation process, noise is inevitable, we proposed two methods to improve the noise robustness of the system. Using restriction algorithm which has strong noise robustness, ESPIT and musical algorithm has better anti-noise performance than annihilation filter algorithm. where estimating pairs with a noise element increases properly the sampling frequency, which should be greater than 2 times the filter cutoff frequency, and we can use the more samples to estimate the parameters. We also proposed a Handwave Prototype based on this sampling structure based on NIPSI adjustments. This Handwave Prototype includes 4 stages: signal generation, analog pre-processing, signal sampling, and parameters estimation. The functions of these instruments are as follows: NIPSIE 1062Q PSI chassis provided containers for other PSI devices. NIPSI 6251 signal generation, run output the RAM. NIPSIE 8133 controls the operation of the entire system. NIPSIE 6363 signal sampling. Next, we introduced several MATLAB simulation experiments, and the experiment parameters were set as follows. Simulation Experience 1: Feasibility analysis of sampling method without noise. In this simulation without noise, we verify the feasibility of the system and prove that it can restrict the unknown parameters of the signal through the samples. We compared the experimental results with the classic FRI sampling system. The experimental results with ideal LPF can be shown in the figure. Ideal LPF and the experimental results with non-ideal LPF can be shown in non-ideal LPF figure. The figure of ideal LPF proves that this method can restrict unknown parameters, and it is obvious that with non-ideal LPF, the restriction results of proposed system is close to the orange parameters than that of classic FRI system. Simulation experiments 2. Comparative experience of sampling methods in noisy environments. From the figure, we can see the NMSE of proposed system always less than the NMSE of classic FRI system. Run systems with high SNR 20 dB, the FRI system using denoise ESPIT algorithm close to the proposed system, which use the annihilation filter algorithm. When the signal-to-noise ratio of the system reached 6 dB, the proposed system using annihilation filter algorithm keeps its steady, and the proposed system using ESPIT algorithm has the smallest NMSE. In this paper, we proposed a FRI sampling for ultra-wideband Gaussian process based on non-ideal LPF, which has 2 channels. With the 2 channels, we can obtain parts of Fourier coefficients. Run processor loss by the new estimation algorithm. Finally, we can obtain the Fourier concessions without no-ideal effects caused by no-ideal LPF. We also designed a hardware implementation system and several experiments to validate the feasibility of the proposed system. Thanks for your listen.